Okay, get this. What if the delicate, branching pattern of a fern could actually power your next smartphone? It sounds like science fiction, right? Well, today, we're diving into the seriously cool and beautiful world of fractal electronics, where we're literally borrowing nature's own blueprints to build the circuits that run our modern world. So let me ask you a question. It kind of sounds like the start of a bad joke. What do a snowflake and a microchip have in common? I mean, really, what could a fragile little ice crystal possibly share with the silicon brain inside your computer? Well, the answer is a hidden language, a mathematical secret that nature has been using for billions of years, and we're only just now starting to figure out how to copy it.
And that secret? It's called a fractal. A fractal is just a pattern that repeats itself over and over and over again at smaller and smaller scales. Just picture a tree branch, right? It splits into smaller branches, which then split into even smaller ones, but they all echo that same fundamental shape. You see it everywhere once you start looking, in a jagged bolt of lightning, the veins of a leaf, and yeah, even in a head of broccoli from the grocery store. It's a way to pack infinite detail into a finite space.
And here's how we can take that idea from nature and translate it into pure math. This right here is called the Koch curve. You start with just a straight line. Then you apply a simple rule, pop a little triangle in the middle. Now you just repeat that exact same rule on every new, smaller line segment, forever. And here's the wild part. The result is a line that is literally infinite in length, but it's all crammed into this one small contained area. This very idea, infinite length in a finite space, is the absolute key to everything we're about to talk about. So what if we took this blueprint from nature and started building our electronics with it? I mean, what actually happens when you ditch the simple squares and circles we normally use and instead build our capacitors, inductors, and resistors using these mind-bendingly complex fractal patterns? Let's kick things off with a component you've definitely heard of, the capacitor. Its job is to store electrical energy. A normal one is basically just two flat metal plates sitting near each other. Simple, but a fractal one, well, it's a whole different beast. Just look at this thing. Instead of a solid plate, it uses a pattern called a Sierpinski carpet. It's like you take a square, you punch a hole in the middle, and then you do the exact same thing to all the smaller squares that are left over. The best analogy is this. Imagine taking a giant, flat piece of paper and just crumpling it into a tiny little ball. You still have all that original surface area. It just takes up way, way less room. And for a capacitor, surface area is everything. It's the whole game. The more area you've got, the more charge you can pack in. So by using these fractal designs, you can massively increase the effective surface area without making the component itself any bigger. And this graph right here shows you the payoff. It's plotting something called fractal dimension, which is just a fancy way of saying how wrinkly or complex the pattern is against the amount of charge it can hold. So a simple line has a dimension of 1. A filled-in square is 2. As our fractal gets more and more intricate, its dimension inches closer to 2, and as you can see, its ability to store charge doesn't just go up, it goes up exponentially. It's a huge improvement. Okay, so let's apply that same exact thinking to another component, the inductor, which stores energy in a magnetic field. Now with an inductor, the most important thing is the length of the wire. A longer wire equals a stronger magnetic field. So what did the researchers do? They used that same Koch curve we saw a minute ago to lay out the path for the electricity. Every time they repeat the pattern, they're folding a longer and longer and longer electrical path into the exact same tiny footprint. And the benefit is pretty obvious, right? You get a much longer effective wire crammed into a tiny space. That means you get a huge boost in inductance, which is just the measure of its ability to store magnetic energy. And once again, the data speaks for itself. As the fractal dimension of that wire's path gets higher and higher, as it gets more complex, the inductance doesn't just increase, it absolutely skyrockets. We're getting way more performance out of way less physical real estate. All right, and to round out our trio, let's look at the fractal resistor, the component that, resists the flow of electricity. This beautiful pattern is called a Sierpinski gasket. Now imagine that every single line segment you see here is a tiny little resistor. You're not just creating one single path for electricity to follow. No, you're creating an entire complex self-repeating maze for it to find its way through. And the results is something totally new. See, in a normal resistor, the resistance is basically just about how long the wire is. Longer wire, more resistance. Simple. But in a fractal resistor, the resistance becomes a function of the network's actual geometry, its fractal dimension. It's a completely different way to control electrical flow. Now, check this out, because the effect on the current is pretty fascinating. As that fractal dimension goes up, meaning the network gets denser and fills more of the space, it actually creates more parallel paths for the electricity to take. So counterintuitively, more current can flow through. You can literally tune the electrical properties just by tweaking the fractal's geometry. So, okay, we've got these incredible new components built on fractal geometry in space. But this is where the research takes a truly mind-bending turn. The scientists behind this started asking, what if we applied the same fractal logic, not just to space, but to time itself? And that brings us to the concept of fractal time. So I want you to forget the smooth, steady, continuous ticking of a clock. Instead, I want you to imagine time that has gaps in it, time that stutters forward in a sort of self-similar pattern, kind of like a song that keeps skipping. It's a mathematical tool, really, for modeling things in the real world that just aren't perfectly smooth and predictable. Probably the best way to think about it is this. Normal, everyday time is like a river that's flowing smoothly and continuously. Fractal time, on the other hand, is like trying to cross that same river by hopping from one stone to the next. You're still moving forward, sure, but your progress is gappy, it's irregular, and it's defined by the weird pattern of the stones. So here comes the grand experiment. Let's take our fractal capacitor, our fractal inductor, and our fractal resistor, and let's wire them all together into a standard RLC circuit, which is a super common building block in electronics, used for everything from radio tuners to filters. And then, let's see what happens when we run this circuit not on a normal clock, but on this bizarre new fractal timepiece. So what on earth happens when you combine fractal geometry in space with fractal dynamics in time? Well, the results are strange, and they are profoundly powerful. So here's what the researchers found. First, we already know the fractal components are just flat out more efficient. But when you add fractal time into the mix, the entire behavior of the circuit gets sort of stretched out. The natural oscillations slow down, and the rate at which energy is lost also slows down. Now, this gives us an incredibly powerful new tool. It means we can start to accurately model really complex systems, like the slow, messy way a battery degrades, or even the unpredictable electrical signals firing in the human brain, things that just don't play by the simple, smooth rules of classical physics. And, don't just take my word for it. The authors of the study themselves said it best. They concluded that the very geometry of these parts, their fractalness, fundamentally changes how they behave over time. We are literally tapping into a new set of physical rules here. So it just leaves you with this incredible question. If we can build electronics that operate on a totally different kind of clock, what else is out there? What other fields, from material science to AI, are just sitting there waiting for us to apply nature's own infinitely complex and beautiful blueprint?